Get started with the afternoon session. So we have a talk and then a break and then 2 talks in the afternoon. They should be awesome. I think we're missing our person, so I'll hand it over after this, but this is an easy one for me. Next speaker is Luke Zettlemoyer. Luke is, well, my favorite professor. He is professor at University of Washington and works at Meta. He's been kind of central to the development of modern NLP, from things like Elmo to Roberta to BART to recent inventions like QLoRa. He's kind of consistently pushed forward where these models are and how to connect language with machine learning. So excited to have him here.
Yeah. Thanks, Sasha. That was awesome. And just because we're academic siblings, you don't have to say such nice things. And thanks everyone for having me. This talk is a little bit of a whirlwind of a few different models we've been doing recently, and it covers language models, it covers image understanding, it covers image generation. And so I think probably I had to learn a whole bunch of stuff, and some of you may not have sort of background in some of the areas, and so. That's fine, and I didn't exactly know how to prepare for that. So I was hoping we could keep the interactive vibe of the earlier talks, and you could just stop me and ask me questions, even really basic ones. I might be screwing up or leaving out some definitions or something. Be super helpful for me. But I'll tell you about some fun models, and in particular, our goal. A lot of folks at Meta and University of Washington did this work. I'll try to credit them as we go, but I want to in particular credit Lily, who I kind of stole 90% of the slides from. All right, so our goal is a simple single architecture for all modalities. So actually really, with some exceptions in the talk, I'll talk about some other modalities, but largely it'll be images and text. But the idea is, we want a single architecture that you can throw whatever data you want into it, and it will be able to do generative modeling on it. Okay? One way to kind of visualize this, it's become a little bit popular even in the last few weeks with the new GPT-4o and Gemini 2.5 releases, where they highlighted some of their kind of mixed modal generation capabilities. We've been doing this work for about like a year and a half, and some of the models that I'll talk to you about were trained about 18 months ago. But these are the kind of outputs you can get from the models. So, it's just an arbitrary sequence of interleaved text and images that forms like a multimodal document. Okay? You could also work on speech, you could also work on other things, but this is really the mindset is like, this is just a sequence of data, just like text is a sequence of data, just like image is a sequence of data, we can sort of model it all jointly, and we can try to get very general architectures. If you can do this, there's lots of cool things. So this was the Gemini 2.0 demo where, our chatbots that we all know and love that have changed the world are now getting very multimodal. So you're seeing images not only understanding, but also generation. So here the model is doing tic-tac-toe and actually kind of drawing new stuff as it goes along. So it drew those extra X's and so forth. We had a paper which I won't go into much detail on, but another great use case for these types of models is visual chain of thought. And so the idea here is if you're trying to solve a geometry problem, you can just have the model go draw lines and like look at it, like a person would, and like sketch things out and play with it, and see if it can figure out how to do reasoning by, actually drawing in a workspace or a sketch pad. And then, similarly, this goes on, but there was a recent meta model called Metamorph where you could sort of start to integrate some reasoning patterns. So the national flag of the country Yellowstone National Park is located in, it does a little chain of thought, and then it spits out an image. Okay? And this is all just sequences of data to us, and we want to try to figure out how to model them. There have been a lot of architectures doing this. This is the Gemini figure from the Gemini 1 paper. Sadly, over time, and especially in the last year, people don't really talk about the details of what they're doing anymore. So I'm very motivated by open science and be able to share what we're working on. And so I can't claim that our architectures are perfect, but I can at least tell you what we did, and we can try to learn from it. Okay? But even in Gemini 1, we already had this idea that you have this input sequence, which is multiple different modalities. In this version, they had different decoders for when they were doing generation that were modality specific, which is kind of where things were there. I'm pretty sure by now everybody's got also a single decoder, or they sort of play different tricks depending on what efficiency they need. But in this talk, we're going to try to unify this as much as possible. So we'll also do sort of single input, but we'll also try to get single output as much as possible. a little bit of background on image generation, which probably most folks know, but it's going to be really crucial to how we set up the two models. There are roughly two different types of image generation algorithms. There are diffusion-based algorithms, and then there are discrete token-based algorithms. And this was kind of the big divide between DALL-E 2 and Parti back when there was sort of a split. Largely, diffusion-based models have won, and I'll show you some sort of evidence for why that might be true. But the token-based models are still around, and people are still working on them. And the way you model with them looks a lot more like a language model. So that's the issue we'll kind of talk about and explore in the talk today. And we'll do some contrasting between those back and forth. If you want to do the token-based approach, you're going to basically think about training something like a VuKGAN. And this is just a figure from a paper. The setup here is that you're going to train a tokenizer. It's not going to be part of your final language model training. It's just a pre-processing step. And then every image, you'll be able to convert into a sequence of tokens that are discrete. We'll use about 1,000 tokens in the talk today. And then you'll be able to convert those discrete tokens back to a reconstructed image afterwards. And this is trained as an autoencoder with a reconstruction loss, all kinds of cool tricks. But it's a discrete bottleneck, and that's the ability to do the encoding and the decoding of the image into a discrete space is what's going to enable all of our joint modeling later. If you haven't studied diffusion super carefully, you might not realize that basically the same thing is going on in diffusion, or I should say in latent diffusion specifically, but you just don't discretize the tokens. You leave them continuous. So again, if you're going to do a diffusion model and generate an image, you're going to pre-train an autoencoder that can take an image, map it to a sequence of patch embeddings. It could be 2D, but let's say a sequence of patch embeddings. Those are continuous. And confusingly, if you're a vision person, you often call those tokens. So if you're ever talking to a vision person, they say, oh, this is my tokenizer. It's usually not discrete. It's usually continuous vectors. Okay, so I've had like tons of confusions about this. But anyways, you go to continuous vectors, and then you can reconstruct to the original image. And there's been lots of work on various different ways of doing this that do better and better reconstructions. But you have that latent space you can work in. And then you typically train your diffusion model in that latent space. Okay, so those are sort of pre-processing steps that I'm going to assume and talk about as I'm going through. But we're mostly just going to assume we're using one of these two approaches and then talk about how to build models on top of them. All right? I'll take you through 3 different models today. So the first 2 are roughly going to be discrete tokens versus diffusion and how to integrate them very tightly with a language model in the 2 cases. And then the last one, with whatever time we have left, is a variation on mixture of experts that's multimodal, what we call mixture of transformers. That allows you to get a lot more efficiency in your training. Any questions about the basic setup before we dive into the models? All right, so to quote someone that's had more impact than me by far, the fact that language models are kind of considered only useful for text seems sort of like a mistake. And really, if you look at any data, you should be able to think about discrete forms of it. You should be able to apply these models. So everything we've been talking about today, this whole week, you should just be able to apply the GPT recipes to it and see what happens, right? And so we started a project long before this tweet was done, but we have been working on a project in this direction. And this is basically the tokenize-everything approach to these multimodal models. And then it will end up with the Chameleon model at the end of this. And in the tokenize-everything approach, what I do is I just look at my data, whatever form it is. In every image, I just run that discrete tokenizer on it, and I say, OK, what used to be an image is now 1,000 discrete tokens. And the vocabulary is not that big. So the token vocabulary would be like 3,000 or something, roughly on that order of magnitude. Okay? And now, once I've converted all of my data, those original multimodal documents like I showed you, I've converted all to just sequences of discrete tokens. Then I just apply the GPT recipes to it. And I get multimodal models. Okay? Say again?
Raster order.
Raster order. That's right. The image will be generated raster order. So technically, the detokenizer has global constraints. So you generate the tokens left to right, but then there is some global constraints in the detokenizer that are both bidirectional. OK, so in particular, I'm just going to go through this relatively quickly, but I'll give you glimpses of different things. We did sort of a series of work here. We looked at how to do pre-training and how to scale it up. We looked a little bit about alignment. We just did really simple supervised fine-tuning. There's been so much work since then on the text side. Probably, all of that would work here too. And you can even do things like, retrieval augmentation or whatever your favorite trick is for LLM. It's going to work in this setting too with very, very high likelihood. So this is a really nice benefit as kind of a model. And so to train the model, I've kind of already said this. You just follow the GPT recipes. But actually, in our work, we even just took the Llama code base. And you use the exact same code, the exact same architecture, everything. It's fine. Okay, I'll show you in a second. The scaling it up actually became very finicky and hard. But the code runs, and everything is well-defined. And you can train the models this way. And the data is any arbitrary sequence of interleaved text and images. You can also do speech and other things, too. And then for inference, again, it's just the same thing. You just do your beam search or whatever your favorite algorithm is. And then whenever you get your sequence of image tokens, you'd run it through that detokenizer, and you get back out your image, and you're good to go. OK? So I've got a series of, I think 3 or 4 or 5 slides doing little vignettes of projects that we did in this space to give you a feel for sort of how these models go. And then I'll get into the scaling, get into some of the limitations, and then we'll switch to the diffusion version of them, which will have some nice properties. Okay? Yeah. So is the tokenization lossless? And the discrete version, actually both versions are lossy, but the continuous version will have less loss than the discrete version. So this can be quite lossy.
So when you do the naive detokenizing, is there such a thing as a naive detokenizing where you get roughly the image and then it's sort of just cleaning it up, or?
Yeah, so could you do some sort of naive detokenizing where you get a rough image and then clean it up? People have done models like that. Yeah. And in particular, you could keep a token-based approach, and then you could run a small diffusion model on top of it, or a super resolution model or something. Maybe it would clean up the faces, clean up the fine detail on the fonts of the text. That's a viable approach. We don't do it here. But if you were building a product, you could do that for sure. Yeah, and it would be very practical.
So I see one difference in the sense that usually in images people use fixed length patches, right? So fixed length tokens. While in, I guess, text they use variable length, right? In the word hello, maybe HEL are one token, while for understand maybe UN is a token, right? So how do you compromise these two?
Yeah, great question. So to paraphrase briefly, text is typically variable length, and transformers are really good at that. You didn't say that, but that's where transformers shine. They're really good at that. And then images are fixed length, and maybe even it feels, this is me adding context, maybe it feels like a little bit overkill to be using this whole autoregressive machinery for something that's fundamentally kind of fixed length. That will factor in when we switch to diffusion. I'll come back and talk about it a little bit more. The cool thing is it just works. Actually, we don't put any constraints into the system to even tell it needs to generate 1,000 tokens. Because in LLM, every time it's ever seen a start image token, it was always followed by 1,000 tokens. It just learns that real fast. Right? So even there's sort of a lot of structure in this data that we're not taking advantage of, but the model just kind of learns it, and it's OK. But it does feel like a missed opportunity, I agree. You could imagine better models that take advantage of some of this stuff. And the diffusion will be one such instance. Let's see another hand. Are we good?
So the fraction of images that you have in the probably depends on kind of the source of the text. If there's a book, maybe you don't have any image in it, and otherwise you want to have images. So this is supposedly learned also from the interaction or from the data set, or how?
Yeah, so that's right. So the question is kind of how do you balance the fraction of image tokens versus text tokens? And the answer is that's the dark magic of pre-training. And even for text-only models, you have to be very, very careful about your data mixes and data balancing. And it's only worse here, but it's not that bad. I'll tell you exactly what we do when we get to the training part. But yeah, you've got to do that by hand. And one last one, and then I'm going to push forward.
You already answered this. Is the detokenizer and the tokenizer trained along with this?
Yeah, so the tokenizer and detokenizer are trained separately as a pre-processing step and then fixed. And that's something we'd also love to train jointly, but that's where we are. Yeah. OK, let me push forward and stop me for some more questions. But let me just give you these kind of vignettes of some interesting things with this model. So to prepare to try to train a bigger model, we had a whole paper in 2023 where we did scaling loss for multimodal competition. And so here we tried to actually look a little bit more at modalities. So we considered images image-text pairs, text, speech-text pairs, speech, code, and molecules as different modalities. And then we would mix them in different proportions. And we would try to figure out, what are the scaling laws? How do you get the right mixtures? And in general, like, are you going to get competition within the single model across the different modalities, or are you going to get synergy, where like adding more of one modality will actually help the other? And I won't take you through all the results, but you get these sort of power law with all these, you get a few extra constants in here to account for modality-specific behavior. But this looks like a pretty familiar power law you may have seen before. And to a first approximation, for small model sizes, you do get a lot of cross-modality competition. Like adding modalities makes everybody worse than just having unimodal models. But the scaling laws predict that if you get up to a certain scale, you'll start getting more synergy. So if you can scale the models big enough, the cross-modal competition won't hurt you as much. Although I don't know that we've seen that a lot in practice, but that's what it predicted.
But your data scaling is somewhat different from what I would expect from like Chinchilla or something. Like maybe for 8 million you're using 5 billion, but for 30 billion you're using just 100 billion.
That's right. So I think these models are a little undertrained. That's right. I think the models are a little undertrained, but you get the compute budget.
Right?
Yeah, you get the compute budget you get.
Therefore, these conclusions may.
Yeah, that's right. And actually, if you're interested in scaling law, we just had an unrelated paper from 2 of my students that we just posted with a nice survey and sort of overview of how to do it. It's really, really hard to get the details right in your scaling laws.
So if you were to scale up from 100 billion tokens to, let's say, 1 trillion tokens, would you just add more images, or would that be challenging because there's not enough images to add?
I've got a handful of slides later on scaling. I'll show you exactly how we did it. Yeah.
How exactly will you evaluate, like with language models, we evaluate the perplexity tokens. What happens with the images?
All right, so for image generation evaluation, so here it's all perplexity. So remember, because we're doing discrete tokens for images, we can do that, but it's suboptimal. It's not the best thing to do. What you'd really want to do is generate the pixels, and then there's a bunch of sort of clip score type metrics that people have used, and they're also not perfect. It's a very hard problem to properly evaluate image generation, but at least you can use kind of standard best practices. Or you could do VQA on top of it or something else. But in here, we just kept it simple. Yeah, it's a good question. All right. So pushing forward, and these were relatively small models still at this point. We also did some of the early work on doing sort of massively multitask fine-tuning of these multimodal models, where you can have any combination of text and images on the input or the output. And so we got lots of different kinds of tasks, image editing tasks, captioning tasks, image generation tasks, and did a really nice study and looked at all the different variations. Lily led this work, and the models are very controllable. And so I refer you to the paper for all the details, but you sort of expect to see higher quality images these days. This is a little while back, but the control is there. So here's the input image. So the setting here is image as the input and text as input, and then this is the output, right? And so you can see you can control it, with these little lines, businessman, boy running in the grass, and it kind of has to match the image and also follow the prompt. Okay, and there's many, many other versions of these tasks, but the cool thing, and sort of, it took a fair bit of work by a big team of people, but we were sort of able to go through and replicate everything you would expect to happen for language models is also happening in this multimodal setting, which is good. The massive multitask fine-tuning works. And then, Michi, when he was an intern at Meta, did a really cool paper showing also, retrieval augmentation works. So you can retrieve from image caption pairs, put them in context, just like RAG is a standard toolkit for LLMs, and this multimodal LLM also works. And so the setting here is these are 2 baseline models. If you ask them to produce a Ming Dynasty vase, you'd like to see something like this with lots of blue and white in a certain shape. But the models don't do that. This is kind of long-tail visual knowledge that they haven't learned. Probably models these days can. They're much bigger and trained on much more data. But at the time, they had trouble with that. Sorry, the actual prompt is the Ming Dynasty vase with orange flowers painted, right? So this should normally be blue. This requires a little creativity to think about how to do it. The models only do the orange. But if you show it an example, you retrieve this and you show it that in the context, then it's able to do much more interesting hybrid things. And similarly here, when you ask it to do Armenian church, that's a very particular type of steeple on the church. The models don't have that long tail knowledge, but if you retrieve that image, put it in the context, the models can copy and actually get it right. Okay?
Does it also understand numbers, like say I want 3 faces or something, or like say 2 men, one is taller than the other one? Does it understand something?
Yeah, so the question is about how does it do with numbers or maybe spatial relationships, taller, even left-right is actually quite hard. So these discrete token-based image generation models have trouble. They do really well with like one object centered because they have enough sort of capacity for that. They do really poorly with fine detail and lots of objects. Even diffusion models struggle with counting, although they're getting better. So that's kind of an open challenge for the whole field. But it's, I think, even worse for our models. And these are a little bit old models, from a year and a half or something. Yeah.
I'm wondering if these models also underwent like RLHF during this process, or it was just...
Yeah. So, I think when we were doing this massively multitask fine-tuning, which is, sometimes you see right before the RLHF, that's when the whole RLHF for text only was exploding, and we just kind of never got to it. So my prediction is that you could do RLHF here and get a whole bunch more gains, but we just kind of never got to that next stage of the post-training. And in general, the multimodal post-training, is not nearly as established a field as text only. So there's a lot of open stuff to think about. One more?
Yeah, so you mentioned that this is retrieval augmented, but as in context means you counted like a
Yeah, so I only did one slide on this, but the way it works is that the data store is image caption pairs, and you use a clip model. You embed the caption, you embed the image, you average them, you put in a data store.
So it's trained on the left-hand side images. They've seen it.
This is just an inference slide. So I'm just showing you, like, if I get this as an input, I can retrieve this and generate this.
Okay.
Yeah. In the model, you can do the model just like you would do RAG for text. So you can actually train it with retrieved stuff in context if you want to, but you don't really have to, and it can learn to do that.
So you mentioned these models are only good for single object.
Well, so that's where they're going to do the best. Yeah.
Right. So during the training, do we also provide multi-objects?
Yeah, good question. So again, we had to curate the data for our own training and for pre-training and stuff, and so almost certainly part of the reason is because of the data we gathered. And I know that like really good image generation teams will specifically upsample multi-object data to try to get enough coverage, and that's kind of a data balance thing. Just like in text where you need to be really, really careful, that also comes up in image gen for sure. Yeah, that's a good question. Okay, so we had done all this work, and we've got some reasonable, like we know the recipe's working, but in many ways, like the real exciting thing about the GPT recipe is that it scales. It's kind of like one recipe in the world that actually scales. Right? So let's try it here too and see like how much can we scale. So this was around the time that Llama 3 was happening internal to Meta, but the only sort of external model to compare to was Llama 2. And Llama 2 was trained at these scales, sort of 2 trillion tokens, up to 34 billion. I think there was a bigger one too, but that's what we could afford with the resources people give us. And so we thought, okay, so can we copy this setup? So we're going to go for the same sizes. We're going to look at various token budgets. The biggest one we do would be 10 trillion tokens, which is 2.5 text. It's, basically we borrowed the data that someone else had used. And then we get a bunch of images. So remember, 1,000 tokens per image. So this is like 1.5 billion images. It's a reasonable scale. State-of-the-art models today would be 8 to 10 billion. And then as much interleaved data as we could get. So these are like those multimodal documents that I showed you at the very beginning. That's actually kind of hard to come by. So what do they add up to? Yeah. Yeah. So we're actually going to do multiple epochs. Yeah.
Was there any upsampling for some of the modalities during
Yeah, so we were not as sophisticated. Given how much language model training has really gone crazy over the last year and a half, there are all kinds of sort of recipes and curriculums and things that you could do here, but we were very, we sort of borrowed, for the text, we kind of tried to borrow what had worked well for others and copy as closely as we could. But for the multimodal, we just kind of had to make it up on our own, and we didn't over-optimize it that much. Because, so much time in the day. But if you had a bunch of GPUs laying around and you wanted to work on that, you could definitely get a better model.
Do you train Chameleon from scratch, or do you pre-train?
From scratch. I'll have some little slides at the very end of the talk talking a little bit about some later models, how we don't train them from scratch. But all of this was trained from scratch. Okay, pushing forward a little bit, training these models was an absolute nightmare. I had a super stressful summer with the team where we kept training at an 8 billion scale over and over again, which is kind of like 1,000 GPUs. And you train on it for like a week or two, and then the model would like slowly diverge. And like really weird things would happen, and your logits would explode, and it was just an absolute nightmare. This kind of stuff, of course, probably OpenAI dealt with this in the early days for text-only models, and then they figured out some recipes that kind of work, and then we all sort of stole them. But I do think in the multimodal setting, it was worse. And I don't think we have a deep understanding of this. Sorry, I'm just showing you. I've got this here. This is what you would like. This is some internal norms of the model. So we're looking at particular parameters. These are the logits at the top, and what you'd like is them to not grow too big. Right? And if you have some internal norms on parameters of the model and it starts growing really big, you're going to be in trouble. You're going to start nanning and overflowing, and your training run's going to be ruined. And we even found that like it would start happening, say, like 30% into training, but nothing would explode until kind of 60 or 70% into training. So you basically just had to throw away the whole run. There's no way to fix it. And we don't really deeply understand why this happened. We did a whole bunch of modifications. I'll use the word hacks. I mean, there's beautiful norms that you can add various places and try to get things under control. But fundamentally, it was a sort of painful process of kind of empirically repeating training over and over again with different things. Part of what was going on is that because the image tokens, the text tokens were all together in one softmax, there's a lot of competition there. And the softmax has a normalization constant, and you can kind of scale up the logits without changing the overall distribution too much. And so there was some sort of craziness going on with some competition. But it's not all that was happening. There's other things happening too, and it's a very messy thing that we don't fully understand, even now. But it made me less excited about token-based models. Okay, so then, this is kind of this is some norms, this is some training losses. And here, you see 150,000 steps into training, so we've burned quite a bit of compute. This is an ablation with and without the QK norm, and what you'd like to see is things keep going down. What you start seeing sometimes is these little divergences where they go up, and this is like really bad, and you lose a lot of sleep, and eventually it'll go totally crazy, and you lose the model. For the 8 billion model, for the 7 billion model, dropout also helped. Whether or not you have dropout in models is like a weird hyperparameter that kind of goes back and forth over time. Okay. So we finally got stable training for the 8B, for the 7B after lots and lots of efforts. And then we thought, great, now we're going to go train a 34B. And of course, it was also super unstable. The recipe, didn't generalize. So the bigger model had more sort of instability issues. Whatever we had done, wasn't enough. And then we had to go add in some extra norms. And eventually, we managed to get some beautiful, stable training out of the box.
So normally with scaling, you would train like even smaller, 500 million parameters, and do lots of them and then scale.
That's
so
right.
That also didn't generalize?
That's right. So the smaller models did not predict the instabilities we saw at 7B. We definitely did a whole bunch of smaller models, including the scaling law slide I had earlier, and those were good. Yeah, it's frustrating.
Did you do some analysis? Is the instability related of how much images you included in your data?
Yeah, good question. So did the text-to-image balance change the instabilities? We didn't play with it too much. Probably it would, but I wouldn't be able to tell you in a predictable way.
So at this point, what is that trade-off you're thinking about of having separate decoders versus?
Yeah, so maybe this is one of the reasons that first Gemini slide had those separate decoders. Actually, maybe it made life a lot easier for them. Yeah, so I'm going to show you how to solve this by switching the images to diffusion pretty soon in a few slides. if you wanted to stay token-based, there probably are other things. If I was going to stay token-based, I'd want to go adaptive. So not just have like a fixed number of tokens for every image, but be able to kind of do multi-scale adaptive. There's some cool models lately coming out in that space. But we've just switched away.
Just to understand this slightly better, like the only thing that's different here, forget that they're images, it's just that they have different complexity distributions in text. Like, so you have two things with different complexity, and that alone causes like massive training head. I think
that's right.
This could even happen if like there were multi-languages or.
That's right. That's right. And actually, that's right. So that it can happen in a text-only model. Actually, if you're having instabilities in your large-scale training of a text-only model, one of the common bugs is incorrect data sorting into your mini batches. So if you don't randomly sort your data correctly, you get too much of the same domain kind of clustered across mini batches, you can get gradient explosions even in text-only models.
Correctly meaning?
Say your random number generator has some, you've done it wrong, and you're getting some sort of biases in the, it's not a proper like full random sort.
Still a thing, like random number generators.
I don't know exactly how they implement it, but you have to get randomness somehow.
No, what I mean is that it's somehow bad, random number generator.
I don't think that it's actually the random number generator. Sorry, that's just a silly example. But for the text-only models, and I haven't trained one in a while, and so the big org's doing that now. But there's all this kind of like mini batch balancing across like how much Wikipedia do you use, how much, and so all that can kind of, if you don't get that right and you don't get the right randomness, it can cause problems. Yeah.
So the text-only models, the model has not seen examples multiple times. Like there's just one epoch. Whereas for these models, like you have multiple epochs.
Yeah, this would even happen during the first epoch. Yeah, the explosions.
I see.
Yeah. And modern text models are mostly taking kind of 4 or more epochs anyways these days. Yeah. So then this is our final hyperparameter setting. I apologize for spending so much time talking about hyperparameters, but it was just a painful experience, and I have to share it with you. If you're on a pre-training team, this is going to happen to you at some point when if you're trying to do anything new and not just trying to do existing recipes. And then, we did the rest of the recipes. So we did, with the bigger model, we did some cool SFT to get it to be able to do lots of different tasks. And we did some kind of evaluation. It was hard to know really, like there aren't good benchmarks for evaluating this generation of this intermixed, interleaved mixed data. But we went and made some benchmarks ourselves. And then we built some baselines with Gemini and GPT-4v, which were the best of the time, where you kind of did image generation as tool use, because no one could really fully do this kind of task yet. But you could have the text model write the prompt, and then a prompt would get fed into an image model, and then you would sort of be able to get a multimodal document that way. And our models, were pretty competitive. We were able to get some pretty good outputs, and we didn't have to do such complicated models. Okay. And I'll skip forward ahead a little bit for time. But there, I have a few slides here, and you can look at the paper. But it works generally. Like the text-only performance is good. Like it's on par with the comparable compute-matched text-only models. The image performance is pretty good. It doesn't keep up with the very best image performance, but it's a very general model that can also do the mixed modal stuff. Okay. And you're welcome to look here for more different details.
Doing like SFT, since it's just like at the top, we can add it like a discrete token, do SFT on a model that was trained on text only, and do maybe post pre-training, like a conditional pre-training or SFT to add this ability to
add the image generation to the model. You could do that, but it wouldn't be alignment scale. So to get a good image generation model, you need to train on sort of billion plus images. So it's a pretty expensive, but you could do it. Okay, let's push forward and talk a little bit about diffusion. So a bunch of issues have come up. I've already talked about all the stability stuff, which was super painful. But great question earlier about like the irreducible loss. So if you're doing discretization, you're doing a sort of a form of quantization, you're just not going to, always going to have some loss on the image. And so because they're so fickle to train, and because we know there's this irreducible loss anyways, and actually this is kind of a discrete versus a continuous model, carefully controlled. It doesn't matter exactly what task. So not only is there kind of a gap, so that's probably that irreducible loss, but the gap even seems to get bigger as the models get bigger. So the continuous models can kind of scale better. And so let's think about, how would we do something that's kind of the beautiful thing about a token-based model is it's very streamlined. I call it early fusion sometimes. It's just like all the modalities are mixing, like as soon as they get in the model, it's all very beautiful and integrated. How do we stay as close to that as possible, but just admit that diffusion is really good for images. They have fixed length there. It's in a continuous space. It's the right thing to do. But you got to think about how to integrate it as deeply as possible and sort of get as streamlined of a model as possible. And so I'm not sure we've done that perfectly, but we did a version of it. And what we did actually is, you just take your image patches. These will get fed into a continuous tokenizer this time instead of a discrete one. And we say, OK, actually, this is still just a sequence of data. So we're still going to have one transformer. But we're going to just kind of multitask train it. So the continuous tokens that are associated with the image will have a diffusion loss on them. And if you don't know kind of how diffusion losses are typically trained, in the end, it's going to be this multi-step process where you diffuse an image. But each image during training is just kind of one step of that process. So you would put kind of noise version of the patches down here, on-noise version of the patches up here. And then you just use your diffusion loss. And then for cross entropy, for the text, you just keep your cross entropy loss. So one single streamlined transformer, but two different losses.
Is there some conflict between the fact that the texts are not noisy, but the images is at a given level, and so the text doesn't change?
Yeah, good question. So is there a conflict between the text not being noisy? We didn't see anything like that. I mean, the tokenizer for the text embeddings are learned jointly, right, in the language model, whereas the image embeddings are kind of fixed, right? It's that tokenizer that's trained in advance, and then noised at various levels.
But I mean, you're going from something that's not noisy to not noisy for the text, and something that's noisy to, not noisy to noisy, or sorry, the other way.
Yeah. So maybe, I think there is some work on noising token embeddings and getting more robustness out of it. Robustness to paraphrase or adversarial stuff, but I'm not super up to date on that literature, and we didn't try anything like that here. Maybe it would help, but we didn't see too many practical issues, and we didn't get to it. Okay, so that's kind of the training story. Super simple, just one transformer for everything. But then, what's the inference story? Well, okay, so the inference story is you can generate from just like a language model for the autoregressive, token. You can do beam search, whatever, sampling, token at a time. But then when you hit your beginning of image token, the model is like a mode switching model. So it just fundamentally switches to a non-autoregressive mode. It lays out however many patches each image has. And now you start doing a diffusion process where you cycle through, you put in noise at the bottom to start with, and you cycle it. But the cool thing is, because it's the same transformer, all the attention layers in this transformer, which Yoon so good reviewed this morning, so we all know the details of what's in this box, they're all attending to everything. And if there are previous images, fine, it would attend into there. It's just one sequence of tokens. It doesn't matter, right? And then after that process is done, you can switch back and forth, back and forth, back and forth.
You do multiple steps, or it's just one step?
Yeah. So I'm blanking on what T is here, but you do multiple rounds of the diffusion process. There's a lot of research in the image diffusion community on making T small, so they can get it down under 5 now. We didn't use the sort of best version. I think ours is kind of 10s. I'd have to go look. I'm forgetting exactly what T was for us, but it's not too bad. But it does involve running the transformer over and over again. Yeah.
Just the image part?
No, the whole thing, yeah. Okay. Yeah, so remember, this part will be, you'll only be outputting, the only thing you'll output is this red patch, but you'll still attend to everything.
Oh, the attention stream.
Yeah.
To align this more with the next token prediction, can the image task be somehow structured as a next patch prediction? Is that something which has already been done?
Yeah, great question. So instead of doing diffusion, could we do like a next patch prediction? And you didn't say it, but I'm going to say a continuous next patch prediction, right? Because if we're doing a discrete next patch prediction, that's the Chameleon model we just did, basically, right? So two big changes here. One is we're continuous, and the other is we're non-autoregressive. You could definitely do a continuous autoregressive. I'm blanking on the name of the model. I think it's AIM. Apple had a model doing this recently. I don't think anyone has gotten a version of it to produce really good images yet. They mostly do it just as like a loss for VLM, where you're mostly focused on the image understanding side. But it's not entirely clear what loss you should use there, and it would be a little bit tricky to get it right.
Just on that iterations, so you have these noisy patches, and then you get the next version, and then could you take those and then as input and then get the next?
Exactly. Yeah. So you iterate. The output from the last round here is the input to the next round, just for the image region you're generating. That's right. Okay. There are a bunch of architectural details that I'm getting so many great questions that I'm going to skip some of these. But I want to give you at least a flavor. So we're going to use a standard transformer architecture. Again, we're going to stick with the Llama one because that's the one we know. You could use something else. But you still, and then we're going to also have this is that continuous image tokenizer, the VAE encoder and decoder. But sort of the output of this is could be 1,000 patches per image, continuous patches. And you can play around with different ways of projecting that output into what you actually feed into the transformer. So you could up-down project them, you could do different transformations on them. And that's kind of our only architectural freedom, because we're going to share the transformer across the text and the diffusion, and we don't want to break the text. But we do get sort of a little bit of playing with our down projection, up projection, kind of the sandwiching that goes around that transformer. We did a lot of experiments comparing just like linear projections versus UNet. If you don't know UNet, it's a convolutional network that's really popular in vision. You could think of it as a very efficient version of things. And in particular, I'm going a little too fast here, sorry, but as you scale up kind of the gap, let's see. So UNet adds a fixed amount of parameters, which is kind of a big percentage when the models are small, but as they get bigger, it ends up being a very small percentage of the parameters in a 7B model, which you can see down here. And that in general, kind of when you get up to the bigger scale, UNet is still doing a little bit better, but the gap is closing. And in general, probably if you continue scaling up, you could get by with just linear projections. But given the compute resources we had here, which were a little bit less than in the last section, sort of our biggest training runs were around 1,000 GPUs here. We were still using the UNets for the very best models. And then one other cool thing is that you get to play around a little bit with the masking. So I said, the image generation is non-autoregressive. I went through that really quickly. But what that really means is, in a language model, we're used to seeing this causal mask, where everything can only look at before it. But actually, on the image part in this model, you get to have a little off-diagonal block, or a little off a diagonal block, right? Because when you're inside of an image, whether you're doing image understanding or image generation, you get to be non-autoregressive, which sort of makes sense. Like that's kind of a reasonable design, because it's always there, right? Whether you're doing diffusion or whether you're doing understanding. And in particular, if you don't do this, your model will perform a lot worse. So here's some different versions of it. I won't go through all the different tasks and numbers. But for image understanding in particular, having a causal mask, which a lot of people have done in the past to try to, when you're trying to do these unified models just because it's simpler, actually can really hurt you in practice. Okay. All right. So we did a bunch of experiments, very directly comparing transfusion to Chameleon. And I'll go through this too quickly. I apologize. But the rough story, I don't have stability graphs here. There's some in the paper. But it was just beautiful. We only went up to 7B here, so we didn't go the bigger. We didn't have enough compute. But all the stability issues went away. The training was super clean and simple. It was so satisfying to see it running after all the pain from before. And you got sort of these nice constant factors. So what I'm showing you here is kind of training flops, like how much actual training you've done for a bunch of different metrics on a bunch of different tasks, some text-based, some image-based. And in every case, you're getting just much, much better scaling trends from transfusion than from Chameleon. We understand why. I mean, I think it's related to the competition stuff we were talking about earlier. It's also related to the irrecoverable loss from the discrete tokens. And just in general, diffusion has got really good recipes for training for images, right? And so when you try to get a new architecture that deviates from that, it's just a really high bar. Yeah.
Question?
Yep.
So in generation, the model decides, okay, now I'm going to output an image, and now I'm going to output a text. It decides.
That's right. So the text vocabulary gets extended to have a new token, which is begin image.
Oh yeah, you mentioned.
So the text softmax will decide when to begin images.
I was wondering if it matters how many, so you mentioned one token which is DOI token. I wonder, does it matter if you have multiple tokens? Does it help or does it not help better generations overall? Just giving the model more time to switch to that spot of doing image generation.
That's a great question. So having more than one beginning of image token. I had to think about this a little bit more carefully when I'm not in front of a crowd, but I think it's actually formally equivalent. I don't think it would matter if you had more than one token. We can talk about it afterwards. Especially because when you switch into diffusion mode, you're going to have all of those continuous tokens anyways. I think it's going to be sort of on the margins whether you have one more discrete token to look at or not. But I'd have to think that through a little bit more carefully. Yeah.
What about the image resolution and dimension? Is it always fixed?
Yeah, so that's right. Our image resolution and dimension are fixed, and different models did different ones, but we're sort of roughly around, I think, 256 to 512 kind of resolution. Yeah. But it can scale up. We basically, there's so much amazing work on scaling diffusion, high resolution, and so forth, and we can just essentially copy all that here. There are some caveats. I'll come back and talk about this a little bit later, but you can do a lot of that.
Can I ask you?
Yeah, go ahead.
So what's the reason that you need the same transformer for both? I was thinking you could have a decoder and an encoder.
Yeah, so why do we want a single transformer? We could even go back to here. It's a good question, actually. And with the mixture of transformer, we're going to start playing around with the idea of not having a single transformer in the very next section with what time I have left. But the sort of motivation here was that if you think back to the scaling laws and so forth, that we're hoping that we're going to get cross-modal synergy, that by kind of putting everything in the same embedding space, you're going to get cool synergies. For image and text, it's actually not entirely clear, like what do we expect to transfer in the embedding space? But you could imagine, for example, you're doing this for speech and text and sort of world knowledge and that kind of stuff transfers. And even for images, there's this long tail, like I was showing you in the retrieval slide, where knowledge about long tail entities, it doesn't seem that that's actually working, but that was part of the goal. Another part is just simple, it's a very subjective thing, but it just feels better to me, which I know is not good science. But we all have to make our bets somehow, right? Yeah, although in the end, we're actually probably not going to stick with it going forward, so it is what it is. Okay, let me get back to do some quick results, and then I want to save at least 10 minutes for the last section. Okay, so here's where we end up. So this is our biggest model. We trained 7 billion parameters, 1 trillion tokens, so we didn't have as much, and 3.5 billion images. We didn't have as much of a budget. But actually, unlike in the discrete case, we only needed around 64 tokens per image, 64 continuous patch embeddings per image. So that actually allowed us to cram it. It helped with efficiency, allowed us to cram a lot more images in at the same compute cost. Okay, so here are some, just for reference, at the time, kind of comparable training scales. And this is accuracy on a whole bunch of benchmarks, and we're doing kind of as well, which is great. So we're doing well on text. And then we can also compare it to what were really good image generation models at the time. This gets a little bit tricky to think about model parameters because often these models are like a diffusion model with a language model kind of grafted on with an adapter, and they only do text to image. And so there's a lot of difference in the setup, but you can still look at the quality of the image generation. And I would say, we were lagging a little bit behind on some of these metrics, but we were kind of shooting distance to being a really good image generation model. And probably, hopefully it would scale up well. These numbers have all moved a lot in the last, about a year since this paper came out. And so, like this gen eval now is in the 80s and so forth. But, we do get some beautiful images out of the model. So these are outputs from the biggest model that we trained. Much, much better image generation out there now. But this does work. So in summary now, we sort of still on our goal of training one unified model for everything, but we've done a mode switching model where we can do diffusion and autoregression.
Do you find it qualitatively different compared to diffusion, like the infamous finger problem or something?
We do not have the finger problems here.
So that's different.
That is different, although I would say that most diffusion models don't anymore.
No, but like this is like fairly vanilla, isn't it?
Yeah. Yeah, that's right. So we don't have to do a lot of the diffusion tricks to solve the sort of. I think that a lot of transformer-based diffusion models get better global coherence anyways compared to the previous kind of UNet style models because they have better self-attention. So we're also getting that benefit, but I'm not sure it's really I'm not sure I can claim credit for that. But it is a nice setup. Yeah.
I have a question about the bidirectionality in the diffusion part.
Yeah.
So it means you don't cache the previous hidden representations or anything, right? So you always recompute. So let's say we have the first image patch.
Yes.
We generate the next one, we condition on that one, right? So now we also attend again to the first one and again encode that one, right?
Yeah, so I think we can follow up on this afterwards, but the question is, can we cache these because they're non-causal in certain ways? And I'm pretty sure we can, although haven't written any code in like 20 years, so I would have to double check with the folks that actually do the coding. But I'm pretty sure we can. And actually, we spend a bunch of time. The hard part here was that Chunting, who's just like a genius, she's amazing, spent a bunch of time building custom CUDA kernels to get this stuff to be efficient because of, we're not in the normal shape. And then, Meta released Flex Attention, and actually Flex Attention can do this for you. And so actually, it's much, much easier to do now. But it was non-trivial. I don't think it was caching so much, but just having efficient implementation is non-trivial.
Cache them if you use bidirectionality. I mean, you would want to recompute them. Right? That was more my question.
Okay, so I'm not sure if you mean like in each round of the diffusion, or if you mean like if there's an image in the context.
Maybe we can talk.
Yeah, we'll talk about it afterwards. Images in the context, you can cache whatever you've done. The image that you're actually diffusing on right now, you'll have to recompute every iteration.
You have about 10 minutes. Do you want to get to the line?
Yeah, sounds good. Yeah. Okay. Okay, so that's the end of the diffusion part. This is a visualization for Chameleon, although you can do a similar thing for transfusion. As much as we are hoping to get this beautiful synergy where like you get this nice alignment of the modalities across in the latent space of this shared transformer, in practice, if you just do simple kind of PCA analysis, and the colors here are different modalities, things kind of separate in the learned spaces. And we haven't really gotten the perfect synergy. And so I think it still remains an open challenge to get these multimodal models to have kind of really, really good sort of cross-modal transfer and synergy. But then, given that they have multimodal competition and other things, we started playing around with sort of a new set of ideas. You could think of it as kind of an extreme version of a mixture of experts. So in the mixture of experts, it's just usually the feed forward, and you're making, you're doing sparsity, you're getting different feed forward, and then you're routing to them. But what we're going to do here is we're going to have multiple different entire transformers, and we're just going to deterministically route them based on modality. So we'll have like an image transformer, we'll have a speech transformer, we'll have a text transformer, whatever modalities you are. And then you're just going to look at what the input token is, or the input patch, and you're going to pick the appropriate transformer. But it will still all be trained, jointly, end to end, with the losses that we were talking about before. And the self-attention will still kind of span. So these will all be sort of compatible sizes and so forth. Everything will still be able to attend to everything. Everything will be sort of globally connected and trained globally. But you'll have just specialized parameters. So like, if they weren't really syncing up the parameter space anyways, maybe that was hurting us. let's try out the other extreme. Let's just separate the parameter spaces and see what happens. Does that make sense? Okay. I will just give you some little vignettes of how this works. That's the entire method. What you see in practice is for the text part, so we compared this MOT approach to just doing an MOE, so a very different way of getting sparsity into the model. For text, the dense and the MOT are just right on top of each other. It doesn't really make any difference. And the MOE actually does better. We know that MOE helps text. But for images, we actually find a much better situation where the MOE is helping image generation, but the MOT is helping even more. So somehow kind of pulling the image parameters out of that shared soup helps the image generation model kind of specialize and learn much, much faster. So like the fact that we were jointly training with the LM was probably really hurting us and slowing down the training. So it remains an open challenge to figure out how to solve this. But if you just want to get the best training possible, you can just split it, and you get this MOT, and it's a pretty good approach. Here are some example images. This is flop matched. So this is kind of everything shared. This is the MOT with the modality-specific parameters. And here you can really see these kind of image generation. You know, this is supposed to be a picture of a long leg, cute, big eye, anthropomorphic cheeseburger, blah, blah, blah. And, you know, sort of, this is on the right path, but that's kind of a weird version. And this is a much more beautiful version, right? Where it's got the semantics a lot better, and it's got a lot better images. And there was sort of compute match. So the fact that we separated things actually helps it kind of hone in and learn that image generation much quicker. Okay. I have a few other slides, but I think that's enough of a kind of glimpse. One last thing is this one. You can now also sort of try to heterogeneously scale the parameters. So, you know, think about it this way. Like, we know that language models want to go up to hundreds of billions of parameters, right? Or you could anyways. And it will get better and better. Diffusion models, actually not so much. You know, diffusion models don't get better above like 10B. Another downside of sharing that architecture is actually that both modalities have to be the same size. Right? So that's not great. One thing we've done so far is, you know, you could just say, okay, well, for the text transformer, that's, you know we need to scale. Let's keep all the dimensions the same, but just go MOE. So we can scale it kind of independently. So the diffusion part, we can just keep dense. The transformer that we do for text, we can go MOE. And then we can heterogeneously like scale the different modalities appropriately for that modality. And we get much better performance doing that. Okay, so I think the jury is kind of out on how to best do all of this, but we're making good progress, and we're kind of iterating through these different types of models. So we saw the Chameleon model, we saw the transfusion model. Sorry, that's just a weird thing. This isn't confidential. And then we saw how to kind of start separating things, and we're trying to really explore like what's really going on in these models, and what should you share and what shouldn't you share, and how do you scale appropriately for each modality, but still kind of try to keep that property where everything is jointly trained and everything can attend to everything very globally. Okay, and so I think we have, unfortunately, you know, more years of work to do here, but I'm excited about this agenda and I'm happy to answer any questions.
How do you think about multimodality as it pertains to like reasoning? You know, like we have this nice story, like we want to ground language in the real world, but like I'd love for that to work. I haven't really seen evidence of this. Do you have any thoughts on that? Like ideally, like, you know, some people are visual reasoners, so maybe some of these models might be better at geometry problems. But yeah.
Yeah, so the question is basically like, how does reasoning port over to multimodal, and how do we get the proper grounding? So, I mean, I have sort of mixed feelings about the word reasoning in general. I'll just be very open. Like, define for me what reasoning is in the first place. To first approximation, I think a lot of the reasoning going on the text side is kind of mimicking patterns that were in the pre-training data.
Maybe like a simpler question is like, does multimodality ever help language tasks? Language
Yes.
only.
Okay, yes. So does multimodal ever help language-only tasks? So there are many language-only tasks where multimodal shouldn't help. Say, you know, more abstract kinds of things. But there should be some where it would help. I think there's a lot of kind of common sense type things. If you actually understand the world better and you have this kind of visual inventory. I think also there's a big push right now towards like video pre-training and then transfer. So there's a lot of kind of knowledge that you need. I mean, in some sense, the answer might be no. Like multimodal is not going to help text that much. But I think it's actually more interesting and nuanced in the sense that like a lot of what we still need for intelligence is that part. Right? So we need like action grounding. We need world models. We need interaction. We need embodiment. And so in some sense, what we need to do is kind of build up that multimodal foundation and make sure it interfaces with the text. And then that's kind of, hopefully these models will be relevant for that, even if we don't make the MMLU scores better. I'll be okay with that. I could still sleep at night.
Is there any shared weights between the modalities?
So yeah, you could imagine sharing weights between modalities, but in our version, we went extreme in just entirely different transformers with no sharing.
Just you concatenate three models, essentially.
So it's not concatenating models exactly. So imagine like in the forward pass, you've got a single stream with multiple modalities in it in your input, and then in your forward pass, these are all running in parallel, and they're all cross-attending to each other. Right? So they're different. So think of it more like MOE, where you have modality-specific parameters, but it's still all one big transformer. Does that make sense? Yeah.
So Emu3 came after Chameleon. I think it worked really well. And do you have any advice on that? Like, it seemed to be Chameleon didn't work, but Emu3 worked, and they didn't do much of any different parameters or modalities.
Sorry, which model after Chameleon?
Emu3.
Emu3. I think that Chameleon was really hard to train, and it wasn't at the same scale as a lot of other really good image generation models. And so it's hard to know how much of it was that we didn't have the right training recipe and how much of it is that we hadn't scaled enough. If you scale a token-based image generation, you can get it to work. You can get really good images out. And so therefore, it would have worked for Chameleon if we kept scaling it and got the stability recipes, most likely, although, who knows. But it's just a lot less efficient. Like having 64 patches per image versus 1,000 discrete tokens is just a big deal. Like it makes a huge difference in terms of efficiency. And so that's kind of the trade-off, although there's some great models that have been still working on like adaptive, discrete kinds of methods, and those are amazing too. And we can chat more specific after.
I'm wondering if you can explain a little bit more about the heterogeneous scaling for image text. You mentioned that the image scales, like it doesn't scale as good as the text. Is that because the curve flattens like faster than text, or the geometries or data?
Yeah, so the heterogeneous scaling that we did, which was just kind of a first glimpse, and you can imagine doing much, much fancier versions of that. But if you look at this picture here, these are different transformers, really, even though they're all kind of going in parallel and cross-attending to each other. So for the text transformer, for its feed forward, we kept this one just as normal feed forward, but for its feed forward, we let it have MOE. So it got more parameters, even though all the dimensions still match, and you can still do all the cross-attention and so forth. So that's kind of cool. And in the future work, I'd love to really explore that more. That's probably a direction we're going to look at. Like, how do you do heterogeneous scaling across different modalities while still keeping everything kind of as jointly trained as possible? Now, the second part of your question about, like, why doesn't image scaling work as well as text? That's just a fundamental sort of fact of the world right now. Like, vision models don't scale as well as text models yet.
Did you have any intuition why?
No. This is a longer discussion, and I've thought a fair bit about it. And even on the image side, image generation models and image understanding models tend to be different models, and they tend to be scaled differently. So even there, they haven't quite unified the two halves like we have on the NLP side, more so. So I don't really fundamentally understand why. It has to do with losses, it has to do with models, it has to do with data. It's lots of factors. For overtime, I'm happy to keep going, but cut me off when I need to be cut off. Last question.
Sorry, I missed or maybe I didn't follow, like in the last architecture, the MOT one, did you have 3 different decoders or?
Yeah. So the way to think about the MOT is it's the exact same. Actually, you can do it for either Chameleon or for transfusion. It doesn't matter. It's the exact same setup. It's really one transformer, but there's less parameter tying going on. So the inference story is exactly the same. You would do the exact same inference in the 2 different settings, but it's just that the parameters that you happen to instantiate here would be different than the parameters that you instantiate when you're here.
Yeah, so if it's the same decoder, is it still like competing still with text?
Is it competing with text? So in the, it is in the Chameleon version where that competition was happening, and it's not in the transfusion version where that competition wasn't happening.
As well as
Yeah. That's right. Good question.
Okay, yeah, I think we should end here. Thank you so much.
Thank you.